So continuing on with our series of videos on finding the volumes of revolution, in this video we're going to cover finding the volumes of revolution using disks or washers when we are generating our regions by rotating around the y-axis. So let's first kind of visualize this with a general set of functions, if you will. So we'll look at this with a washer and realize that the disk, we've kind of already seen it with the x. It's pretty much like having an inner radius of 0, and it's pretty much just a smaller example of a washer. So we'll look at how to visualize this with washers because those tend to be a little bit harder for most people. So let's say that our region is this curve that's drawn here, kind of like a hill. We have G is the red piece and blue is its own function. They are written, just to highlight, this is G of Y. We're not using X's here because how this problem is going to go is if you turn your head, it's going to be pretty much the same thing we did, but rotated so that now Y is kind of like our active variable. And if you rotate the picture, you can see how it's going to be the same thing as what we just did. But in order to rotate, it's like switching the variables. So we would write our functions as functions of y as opposed to x because that's going to be what actually helps us have that effect of doing the same problem as we already did. So if we went ahead and rotated that golden region around, this ith rectangle here is going to become the inner piece of a washer. It's going to generate this washer. And the solid as a whole would be kind of like this, almost like a Rolo, like the candy shape, but hollow. It'll be hollow down until the very bottom when it touches the axis here. So all of them are all the cross sections will be washers. Okay, so when we look at finding the volume of the ith disk and washer, what we need to do is find the area of like the donut top and then multiply by the thickness. So in this case, the thickness is no longer a delta x so much as a delta y because the thickness of a rectangle is a delta y. So when we find our volume of just one washer, we will have area of, we'll just call it donut times thickness. So the thickness is a delta y, and what will the volume be? I'm actually gonna write this. I'm gonna write this in a more spacious area. So the volume will be delta y for the thickness times. Now this is the same shape we were just doing in the last video. So thinking about if we have a washer, we're going to find the area of the big outer circle and take away the hole in the middle of the donut, right? So pi times the outer radius. The outer radius looks like it's going to be, draw here, outer radius looks like it's going to be the distance from our axis to the f function. Pi f of y sub I squared minus pi, and the inner radius will be the distance from the axis to this red, g of y curve. So g of y sub I squared. Okay, and all of that is times delta y. Okay, so cleaning that up when we write the approximate, the Riemann sum is going to be adding from, ranging I from 0 to n minus 1. We have our pi, f of y sub I squared minus g of y sub I squared. That gives us the area of the donut times the thickness is a delta y. Okay, now the same concept is going to apply as n goes to infinity. Our thickness, our delta y, will go to 0. And to get our exact integral, we will get pi f of y squared minus g of y squared integrating with respect to y. And when we look at where we cut our rectangles from to give us our limits of integration, we won't be cutting from left to right so much as the rectangles are going to start being sliced from bottom to top. So it's going to be from y equals 0 until, we'll call this, A to B there. Okay. Okay, leaving it general, I won't call the A 0, even though in this picture the A is at 0. I'm just going to leave it as A to just generalize it. So let's highlight our different pieces. We got the volume of just the ith disc and washer. We've got the You've got the approximate volume from a Riemann sum. And then we have the integral, which will give us the exact volume. Okay, in a disk, this problem becomes even easier because our inner radius is 0. So it's, and just the g of y function doesn't exist basically. And it's the same concept. So let's jump into a couple examples. For our first example, we're going to consider the region in the first quadrant bounded by y equals 2x and y equals x squared, and we will find the Riemann sum approximating the volume of the solid generated by rotating around the y-axis. Then we will find the integral that would give the exact volume. So we're going to focus on just our setup, not so much the computation. Remembering that the computation of integrals, we'll learn a lot of techniques for how to do it in Chapter 7. And in the meantime, you can use tools such as Wolfram Alpha or your graphing calculator to actually compute these integrals if you were to be asked for them. So when I take a look at my region, 2x would be the line with a positive slope of 2. And my parabola would be y equals x squared, so looking like that. My intersection points would be happening at 0 and 2. And the region that we're finding the area of is shaded in purple. And sorry, we're not finding the area of that region. I misspoke. We are actually going to find the volume of the solid generated by rotating it around the y-axis. So I'm going to draw this here. Here's my rectangle. And this point, will be the bottom of the rectangle, is blue. And that little red rectangle is going to be rotated around the y-axis. So the picture here is going to set you up for success. Trust me on that. If you draw the picture the wrong way in this step for what you're doing, all of your work after is going to follow incorrectly. So please, please go slow, be methodic, check your graph. This is the step that's going to determine whether you are understanding what's happening or not. So we have our rectangle that's going to be rotated, and it looks like because there is a gap here between the green line and our axis, this is going to generate a washer. So when I draw the washer, it's going to look like this. I'm actually going to move it down here to give us a little bit more room to label dimensions. Okay, and it's just to establish the fact that it is a washer. I'll shade the inside. So what are we looking at for the thickness of this washer? It looks like the width of the rectangle is a delta y, because you would find how thick it is by subtracting y values. So our thickness is a delta y. And then to find the volume of it, what we're going to need is that inner and outer radius. So the outer radius is going to be from the y-axis to the outside, which is the blue curve, so 2x. Now hold on a second. I almost did something that could be problematic, right? Because I said 2x, but we already set the variable here. We looked at the thickness and we decided that it needed to be a delta y. So my variable is established. So for me to write that the radius is 2x, I've just switched my variables. That's not going to work out. You got to only have one variable. So I need to think of my radii in terms of y. So the outer radius and the inner radius need to be in terms of y. Okay, and that is because of the delta y. That's going to necessitate this. Okay, so when we look at these curves, we need to look at them a different way. If y equals 2x for the green line, then x equals y over 2. And for the blue curve, if y equals, what is it, y equals x squared? If y equals x squared, then this part of the blue curve would be positive square root of y. Okay, how do I know that when you square root, how do I know that that is the positive square root of y versus the negative square root of y? Well, my x values are positive on that side versus this side of the curve would be x equals negative square root y because the x values should be negative in quadrant 2. Hopefully that makes sense. So our outer radius is going to be given by square root of y, and we're doing just a general disk, so it'll be square root of y sub I, and the inner radius is going to be y over 2. And we're doing this for a general ith disk. So there's our radii. And to find the volume of the washer, remember, hopefully this is becoming a little commonplace, that we're going to take away the area of the black circle from the area of the red circle. So the volume would be pi, and then outer radius square root y sub I squared minus pi times y sub I over 2 squared. And all of that is times the thickness of delta y. So there's the volume of just one washer. The Riemann sum is going to be given by adding up the volumes of all the washers. So pi square root of y sub I squared would be just y sub I minus y sub I over 4 squared. That's y sub I squared, all times delta y. That's doing a little algebra as we go along here. And n is the number of slices. Every now and then I forget to write n, and it's the capital N, and it's really important to write that down and establish what that variable means, because otherwise it's just a variable that pops up from what appears to be nowhere, and people get confused by those. So please do write down. If you don't use big N, if you prefer a different notation, just choose a variable and stick with it. The only one that's taken is I and Y, because we're using those for other things. So that is my spiel on why we write that piece. Okay, so for our integral, as we let n go to infinity, delta y will go to 0, and we will get the integral. We are integrating pi times y minus y squared over 4, and with respect to y. Now we need to look back at our picture and decide where are we starting our rectangle. So we work from smaller value to bigger value. So from bottom to top here, we'd start at 0, we'd cut all the way up until we got to the top intersection point of 4. So 0 up until this point would be 2, 4. So from 0 until 4. Okay, once again, the intersection point has y coordinate 4, so we're working in terms of y's, and that's why we wrote 4 there instead of writing 2. And even someone like me who's done this probably 1,000 times at this point has the tendency to switch up X's and Y's. It's very commonplace that we're used to working with X's coming from single variable calc. And as we transition to multivariable calc, we are going to work more and more with different variables. So we have to really think about our variable choice. And before you move on from a problem, the first thing you have to check, you need to check your problem should be all in one variable. Okay, so if I see a mix of X's and Y's, wrong. We can't even do a single integral with mixed variables. And then what variable is it going to be? The thickness variable. So when you look at your disc or your washer and you look at the thickness, whatever variable is giving you that thickness for the disc and washer is going to be what variable you should be working with. So moving on to the next example. We're going to consider the region bounded by y equals e to the negative x, the x-axis, and the lines x equals 0 and x equals 1. We will find the Riemann sum approximating the volume of the solid generated by rotating around the y-axis. Find the integral that would give the exact volume. And to start that off, we're going to start with our visualization, drawing the region. So y equals e to the negative x will be a reflected e to the x curve, and x equals 0 and x equals 1 will be vertical lines. There's x equals 0, and here's x equals 1. Okay. So when I look at this one, it's really helpful to have your arrow for rotation down because this problem would lend itself well to working with either variable. And we'll see which one is actually easier. But anyway, if we rotate around the y-axis and we draw in our green rectangle, we're rotating around the y-axis. So my rectangle is going to be drawn like so. And this problem is actually going to give us kind of an interesting phenomenon that happens. I'm going to blow it up so you can see what it is. When we make this really big, I'm going to erase the shading for a second. And then let's look at a phenomenon that's going to happen here. Okay, when I look at these points, I'm going to draw a dotted line here. Because when I find the rectangles past a certain point, the top of the rectangle and the bottom of the rectangle is going to be different functions. So this black dotted line marks that when I draw my rectangle above that black dotted line, the top function will be our e to the negative x curve, and the bottom function will be the x equals 0, versus when we hit this x value on the pink line, it switches to where the rectangle is found from pink to blue, and those are fairly simple. So we can actually go ahead and break this problem up into two regions, and I'll shade them. So we'll do purple region. We'll have to find this with an integral, and the bottom region is just a rectangle, so that is pretty easy, and we don't really need an integral to find that. Okay, so now that I have that problem split up, let's find the volume of the ith disk, lavender region, And then we'll find the volume of the ith disk. Mint region. Okay, so let's start with mint since it's pretty easy. So the cylinder, or sorry, I should watch that. The disc, when I rotate it around, it's going to be solid. And the radius is going to be uniform the entire time. So the volume of one of those is just going to be pi, and it's going to have radius of, looks like a uniform value of 1 squared times a thickness. You know, again, we're looking at a set single solid. Like the mint green rectangle, we don't even have to add up the cylinders. We could literally just find the volume from that one big disc. So we don't really need to do a Riemann sum for this piece. We could figure out where the pink and red curves intersect here. Where does x equals 1 equal e to the negative x? The y value would be, that's going to happen at 1 e to the negative 1. So that y value, the radius is going to be 1, and the height of the cylinder is just going to be e to the negative 1 for the thickness. So okay, and I don't really need to use variables here because again, that's a simple cylinder to find. So now the actual hard calculus part of this, we'll add the volume of the lavender onto that. Okay. So now kind of going back into our familiar territory, if we take a look at a rectangle in the lavender, the outer radius for that is coming from the red curve. So since our thickness is going to be in terms of y's, our curve needs to be in terms of y. So to solve the y equals e to the negative x for y, remember we can take the ln of both sides. So we get e to the negative x. When you take the ln, cancels out the e function, we get negative x equals ln y. So x equals negative ln y. Okay, so here's our disk. Okay, and it's just an arbitrary disk with a delta y. The radius is going to vary as we go from bottom to top. So our radius is just going to be given by the formula negative ln y sub I, because we're looking at a general disk. So the volume of the ith disk is pi times radius negative ln y sub I squared times delta y. And that's the volume of just one ith disk. So the volume of the whole 3D region, we'll do the Riemann sum. We add up all the washers, pi negative ln y sub I. Making sure that squared is on the outside. Okay, so pi r squared times our thickness, delta y, and our index ranges from 0 until when you stop slicing, and is the number of slices. Okay, so there's our approximate for that lavender region, and then integral. Okay, just reminding ourselves, this is for the lavender region only. As n goes to infinity, delta y will go to 0, and we'll be integrating pi times ln of y squared with respect to y. And we have to look at where will we be cutting, where will we be slicing our discs from. So it looks like we will start slicing the discs for the lavender region at e to the negative 1. And we will continue slicing until we get to 1. Okay, so from the y value of the bottom point to the top point. All right. There's our integral. So if someone says, okay, so what is the volume of the whole region, which is what we were asked for, the volume of the whole 3D region would be, I should label this a little more specifically, sorry. The volume of the whole 3D region, lavender. Can be given by the integral e to the negative 1 pi plus the area for the mint green region. So there is the volume of the whole region. Exactly. Okay, and this is an example of an integral where if I say don't compute an integral, this integral is really going to teach you that, because having a ln y squared, this particular integral would not be something that you have the tools to integrate. We will learn all the tools of by hand integration that we have as humans, and we will understand what technology does for integrals in the next chapter and following chapters. But at this point, for you to sit down and compute this integral is impossible. And your computer is going to use approximation techniques to do it even. So this is truly something like, don't waste your time computing this. If I say like stop at the integral, please do just stop at the integral. Okay, so that's kind of a fun problem. Deceptively looks very simple, but a little more complicated. And the cool thing about this problem is if you compare this video to my previous video on doing these when you're rotating about the x-axis, we looked at the same region and we found the volume of the solid that would be generated around the x, and we can see like the same region rotated around different axes gives us totally different solids, and the ease of computing is totally different. So this one's way harder, like we physically can't even compute this by hand, versus the other one, super simple integral. We could do that by hand just any day. So this concludes our video on finding the volume of solids of revolution around the y-axis. In the next video, we're going to go ahead and take a look at how we can find these solids of revolution using the cylindrical shell method, which is a different method than the disc washer. So same solids, but different method of integration, and I will see you then.